Hello, and welcome to interactive sound propagation for dynamic scenes using 2D wave simulation. My name is Rosen, and I worked on this project as a capstone piece for my bachelor's degree at the DigiPen Institute of Technology in Computer Science and Digital Audio. I collaborated on it with Keith Godin from Microsoft Mixed Reality and Nikunj Raghuvanshi from Microsoft Research. They helped me bring the project from the end of the academic year into what it is now, ready for the conference. They inspired the project after one of their talks demonstrating project acoustics with the Audio Engineering Society, and they gave early and continued guidance on project direction. So diving right in, the motivation for this project stems from the need for immersion in interactive real-time simulations, like games and VR. Immersive graphics has typically taken the forefront using realistic techniques like PBR, GI, and real-time ray tracing with RTX technology. Typically, immersive audio solutions have been relegated to using heuristic approaches that ignore some major components of how sound waves travel differently than light. To be truly immersive, we need cohesion between the two parts of interaction, with consistent audiovisual cues based on dynamic sound sources and listener positions in complex environments. So the main challenges with making audio effects truly immersive is that the immersive effects require diffraction for complex scenes. These effects are occlusion, reverberation, and directivity of the sound sources and the directivity of the listener. The problem here is that robust diffraction effects require wave simulation, and wave simulation is usually too expensive to do in real time. The problem expands further with the fact that modern games and VR have increasingly arbitrarily dynamic scenes. Games like Fortnite and Minecraft allow the player to make and destroy buildings, trees, and even the terrain itself on the fly. Past solutions that have diffraction have really struggled with dynamic geometry like this. So here's an example of our final result working with diffraction effects in a dynamic door occluding a sound source. There's extensive prior literature on acoustic simulation and graphics. We built upon the ideas in Project Acoustics, which is a wave-based technique that includes diffraction effects. We borrow the idea of wave simulations that are encoded and rendered in terms of acoustic parameters such as loudness and reverberation time. But we wish to overcome its significant limitation to pre-computation on static scenes. For dynamic scene elements, the diffraction kernels approach has been recently proposed. Global propagation is done using ray tracing that lacks diffraction. For a few separable rigid objects in motion, diffraction effects are incorporated using their pre-computed response kernel, where they intercept the rays. In contrast, we aim for completely general dynamic geometry with no pre-computation or ray tracing. Prior methods have proposed wave simulation on dynamic scenes, but for offline, high-quality sound synthesis on small scenes. Our aim is real-time propagation on game scenes and trading off simulation fidelity for a fast and plausible rendering. So our solution aims to solve all the problems listed previously with a minimal CPU budget, such that it would be viable for a modern interactive application. So we run a real-time wave simulation on a single CPU core. This wave simulation generates a set of air pressure responses. We restrict the wave simulation to 2D. This allows it to be run on a real-time basis, but it limits it to mostly enclosed floor plans or outdoor propagation. We only simulate on static snapshots, similar to past approaches. We analyze the impulse responses generated above and parameterize them, encoding the response signals into a defined set of acoustic effect parameters mentioned earlier. The impulse responses are discarded, and the parameters are used and interpolated between when rendering the audio. The last thing to note in our solution is that rather than interpolating the scene geometry during the wavesolver processing, we interpolate the parametric simulation result during audio rendering. Because of the 2D nature of the simulation, we've called the solution Planeverb, as it operates on a plane and calculates reverberance. Let's start into the proposed project architecture. So we have 3 threads. The game thread and the audio rendering thread are standard for games and other real-time applications. And the last thread is the one that we have made, the acoustic simulation thread. The game thread runs the player as normal, rendering graphics and running physics while the player moves around. And while this happens, it sends information about the player and the scene geometry to the acoustics thread. The game thread runs at the typical rate of 60 frames per second for realistic, smooth graphical fidelity. The acoustics thread and the game thread have one point of synchronization, where changes to the scene are added to the simulation after each run of the wavesolver. The simulation thread runs at slowest 10 frames per second, which we found allowed for large enough scenes with dynamic geometry while preserving the plausibility of the audio rendering. The acoustic simulation thread will run its 3 steps as fast as possible for the length of the simulation with no limiter. Its 3 steps are 1. Wave simulation, running a wavesolver on a 2D acoustic grid to generate a set of air pressure impulse responses. 2. Parametric encoding, analyzing each impulse response for a set of acoustic parameters. And 3. Scene configuration and rasterization, fetching the most recent data from the game thread and adding the scene geometry to the acoustic grid. Once the simulation thread generates a set of parameters for each point in the grid, sound sources can pull those parameters from the audio rendering thread to be rendered with the DSP required at the typical 44.1 kHz. Let's take a look at the wave simulation part of this. So we use an acoustic finite difference time domain, or FDTD, wave solver in 2D. In essence, we solve the acoustic wave equation listed here and discretize it using Yee's method. We process a scalar field of air pressure and a vector field of air particle velocity. The processing simply propagates a Gaussian pulse from the listener's location in the grid and records the pulse response at each other point in the grid. To avoid conditionals in the main processing loop, we have an adjacent geometry indicator field using an approach motivated by the Aerophones and Flatland paper, which is a 2D FDTD simulation on the GPU. Next, let's take a look at the parameter encoding step. The wave simulation now has a set of generated impulse, or in this case Gaussian pulse, responses for the grid. Using these responses, we extract the main acoustic parameters required to realistically render their propagation effects. These are the source and listener directivity, the direct loudness or obstruction, reverberant loudness or reverberance, and the decay time or the RT60. The parameter extraction is entirely based off of previous work from Project Acoustics with the exception of listener directivity. Project Acoustics uses 4 simulations in parallel for listener directivity. By doing this, they are able to calculate both direct and reverberant listener directivity. Running 4 simulations in parallel is too expensive for the CPU for the constraints of our solution. So Planeverb avoids 4 simulations by keeping track of the initial onset delay of the impulse responses and then uses a gradient descent. The drawback of this approach is that it can only calculate listener directivity for the direct sound and not the reverberant sound. Next, let's take a brief look at the renderer. Taking the encoded parameters from the previous step, we then interpolate them over the course of one audio buffer to smooth the changes frame to frame. Because parameter encoding occurs for all possible source positions, this approach scales to any number of source positions. The rendering pipeline is essentially a simplified version of the paper listed on the slide. In essence, we split the signal into direct and reverberant paths. We apply attenuations to both, then split the reverberant signals into 3 paths to go into the global set of canonical reverb filters. Using this approach, we are able to minimize the number of expensive filters, allowing the project to render a large number of sources. To demonstrate the results, we integrated the DSP and the simulation into a Unity plugin. Despite the project's 2D limitation, we integrated with 3D scenes to show its full potential even as an approximation for the 3D scenes. So quick notes on the Unity plugin implementation. Because we now have a 3D space, we were able to only register geometry for the simulation if it's at the same height as a player's head. This gives some pretty convincing 3D effects. There are two major drawbacks of the Unity limitation, however. The first is that in the interest of rapid iteration, objects in the scene are only sent to the simulation with their in-game axis-aligned bounding boxes. This coarse representation of the scene geometry can definitely be changed and discretized more finely in the future. The second drawback is that because of the original project scope, it didn't include creating a custom reverb DSP effect. Some creative routing of signals from the Unity audio engine was required to push audio from Unity through our system back into Unity for its built-in reverb mixer effect. We had three main test scenes in Unity. The first one was used to ensure that the effects of the project worked with completely static geometry. We have one sound source, which is the sphere, and two walls that create a portal for the sound to diffract through. Let's take a listen. This is the second scene created in Unity. Here we have one wall in the center that slides back and forth, showcasing the ability for dynamic geometry to be used in the scene. Additionally, the sound source now has a forward direction and is set to move back and forth while spinning to demonstrate the source directivity feature. This last test scene was a full test of Planeverb's features in an example game scene. Here we have a sliding door to the alcove in the top left. We have movable occluding geometry, such as the boxes in the top center and the jars in the bottom left. We have a movable radio that plays music, and a man singing in the alcove. Here we are finally able to explore the ability of the plugin to only register geometry at the same height as the player's head, allowing the player to crouch behind the box and jump over the wall of the alcove.
Sadite languisce il cor, mio ben, credimi amen, senza di te languisce il cor, mio ben, credimi amen, senza di te languisce il cor.
So here, we take the scene that we just watched, the man in the alcove, with the sliding door, and we plot both the direct and reverberant signal energy from the simulation thread over time. And we have the width of the portal in meters. The portal width is a smooth continuous curve because it is updated at 60 frames per second on the game thread. However, when accessing the dry and wet energy from the 60 Hz from the game thread, you can see that the energy is stair-stepping up and down. The simulation thread runs at 10 frames per second, as mentioned previously, and the acoustic grid is broken up discretely, meaning this stair-stepping is required. However, notice how closely the curves match, such that with the parameter interpolation when rendering, the effect is perceived, as you could hear in the previous scene, as continuous. To summarize, we've created a real-time wave-based propagation for arbitrarily dynamic scenes on a single core. To process in real time, we've constrained the simulation to 2D and only simulate on static snapshots of the scene geometry. We encode the results with acoustic parameters and render those instead of using impulse responses. This research shows that real-time wave simulation can be a viable, practical path for interactive applications like video games and VR for the future. For the future, we plan to add a parameter for 3D to 2D correction for reverberation. This way we could take ceiling height into account. We want to add an extension into 2.5D in constrained height above and below the listener. We've identified several places for code optimizations, the most major of which is a proper vectorization, which can lead up to a 5x speed increase. There are faster wave solver algorithms, and there's a potential for using the GPU to run the wave solver. Typically, AAA games are GPU bound and don't have much GPU budget available, but for games with a dedicated compute budget, this is definitely a viable path for the future. And thank you for coming to my presentation. All the source code is on GitHub at the bit.ly link provided. Thank you for coming, and stay tuned for more information.